So for thermal energy, we're largely looking at the energy inside the modes. And how much energy does one single mode have typically? Well, not the number of modes, how much energy per mode? Yeah, 1/2 kVt. Because in general, the energy per mode, we expect it to be proportional to the temperature. Higher temperature means more energy per mode. You have to add energy to raise the temperature. And specifically, the energy you're adding gets distributed evenly to all the modes, assuming everything has reached thermal equilibrium. And specifically, the energy per mode is temperature times some constant. And that constant turns out to be 1/2 times another constant called Boltzmann's constant. So the energy in one mode is 1/2 of Boltzmann's constant times the temperature. And that temperature does need to be in Kelvin because it's an absolute amount of temperature rather than a change in temperature. However, we're not just talking about one mode. We're typically talking about some number of modes in a molecule. Like, for example, let's say you've got maybe a nitrogen molecule in, let's say, gaseous form. What modes would you expect that to have? If we wanted to count up all the modes. Well, how would we categorize them? Which modes would we want to include? What is this molecule able to do? And can you be more specific? What kind of kinetic energy? Yeah, we're going to have translational kinetic energy. And also rotational kinetic energy. So it's got translational modes because it's able to move around. It's got rotational modes because it's able to spin. And yeah, it could also have internal vibrational modes. Because it's possible that the atoms might be vibrating against each other inside the molecule. And how many of these would we expect? Like how many ways can the particle be moving? It's moving in 3 dimensions, right? This is a 3-dimensional universe, so it can move in 3 dimensions. It could be moving in the X direction, moving in the Y direction, and moving in the Z direction. So there are 3 translational modes for this molecule because it has 3 dimensions it can move in. But if it's linear in shape, how many dimensions can it rotate in? Yeah, it only has 2 rotational modes. Because even though we're in a 3-dimensional universe, so there are hypothetically 3 axes that something could rotate around. But since this is a linear shape, rotating around this axis works. Rotating around this axis works, but rotating like this doesn't actually change anything. So the rotation around its own axis of symmetry doesn't actually count as a meaningful rotation. So we only have 2 rotational modes, not 3, because it is linear in shape. If it was nonlinear, like for instance, a water molecule, the fact that that is nonlinear in shape means that this molecule can rotate in around 3 different axes in a meaningful way. It can rotate around, let's say, the y-axis, the x-axis, and the z-axis. So all 3 of those rotations would actually count as different meaningful rotations. But if it's linear in shape, only 2 rotational modes. And also, we could include internal vibrational modes. And how many internal vibrational modes would you expect for this diatomic molecule? Yeah, 6n minus 6 would work, although for diatomic, what does that result in? Well, actually, no, 6n minus 6 is for all the modes together. And I think for linear, it would be 6n minus 5. But if you just have a diatomic molecule, how many vibrational modes would it have? How many ways could the atoms in the molecule be vibrating against each other? This one actually works out to just 2, because even though this is a 3-dimensional universe, the bond itself counts as 1-dimensional. If these atoms are vibrating against each other, there's only 1 dimension of vibration. The bond itself is 1-dimensional. It's just a single straight line. So the molecules could be moving along that one straight line. Sorry, the atoms inside the molecule could be moving along that one straight line, and they're also interacting with each other along that one straight line. It's as if they're attached to each other by one tiny invisible spring. And that along that mass spring system has 1 kinetic energy mode and 1 potential energy mode. So this diatomic molecule would have only 2 internal vibrational modes, which is 1 kinetic energy and 1 potential energy. So for any diatomic molecule, it can have 2 internal vibrational modes. However, those are only active at very high temperatures. At medium temperatures and low temperatures, those would be frozen out. There's not enough energy for them to vibrate. But at very high temperatures, the internal vibrational modes would be active. So in total, this molecule could have up to 7 if they're all active. But that's only going to be true at higher temperatures. At very low temperatures, only the translational modes would be active, so it would just be 3. At more moderate temperature, like when you get up to about room temperature, you'd expect the rotational modes to also be active, so you'd have 5. And then at very high temperatures, you'd have all 7 active. But at low temperatures, there just isn't enough energy for the other modes to kick in. Any questions on that so far? And the 6n-6 and 6n-5 formulas you may have seen are actually for the total number of modes if they're all active, specifically 6n-6 for nonlinear and 6n-5 for linear. In fact, we can try that here. This is linear in shape, so we should be able to use 6n-5. What's n for this molecule? What does n represent? Yeah, n is 2, because n just represents the number of atoms in the molecule. This is a diatomic molecule, 2 atoms, so n is 2. And this is linear in shape, so we use 6n-5. 6 times 2 minus 5, 12 minus 5 is 7, which matches up with what we predicted here. So these formulas are for calculating the total number of modes in one molecule if we assume that all the modes are active. And if you want to see where those formulas come from and some examples of how they're used, I go over these in the previous workshop video as well, which you can find on math.ngs.org/P7A. But the important thing about the number of modes is that each one of those modes has this much energy. We assume that, assuming everything's at thermal equilibrium, we can assume that all the modes have the same amount of energy on average. And that amount of energy is 1/2 kBt. So assuming all these modes are active, how would we write out the energy of this one molecule? The thermal energy of this 1 and 2 molecule, how would we convert the energy per mode into the actual energy of this entire molecule? Yeah, we just multiply by 7. We wouldn't actually use Avogadro's number here though, because we're looking at just one molecule. So we have one molecule, that one molecule has 7 modes. Each one of those modes has this much energy. So we'd have 7 times 1/2 times Boltzmann's constant times the temperature. So if you know the temperature, you could fill that in Kelvin and multiply by Boltzmann's constant, which you can look up. That should be some number in joules per Kelvin, times 7 times 1/2. And that'll tell you the thermal energy of one molecule. If you then presumably wanted to figure out the energy of a larger sample, you'd multiply that by the number of molecules. But this would be the energy of one of these molecules. So we can expand this out. The energy per molecule would be that 1/2 kBt, because that's the energy in one mode, times the number of modes. And you could almost think of this as being like a unit conversion sort of thing. If you take a look at the units of measurement, 1/2 kBt, that's just the energy per mode. If you multiply that by number of modes, modes and modes cancel out, you're left with energy. Or I guess formally we should think of this as modes per molecule, because this 7 is 7 modes per molecule. But if we multiply energy per mode times modes per molecule, we're left with energy per molecule. And that's if you want the complete thermal energy of this one molecule. If you were looking for a specific type of energy, like let's say you wanted to know how fast this molecule is moving. If what you care about is how fast the molecule is moving, what are the only modes you'd actually consider? What are the only ones of these modes that have to do with the molecule's motion? Yeah, the translational modes specifically. So if what you cared about is the speed of the molecule, you could calculate the kinetic energy of one molecule by just taking 3 times 1/2 times Boltzmann's constant times the temperature. That gives you the energy of 3 modes, such as the 3 translational modes. So you can multiply 3 times 1/2 times Boltzmann's constant times temperature, and that'll find the kinetic energy of any molecule. The kinetic energy of one molecule depends only on the temperature, because every molecule is going to have 3 translational modes. If you then wanted to find the speed, you would also set that equal to the usual 1/2 mv squared. And then you could solve for speed. Of course, that's going to require you to know the mass of the molecule, but you could look that up on a periodic table. But this can be used to figure out the average speed of a molecule in a system. And note that that only depends on the temperature that the system is at and the mass of that molecule. Nothing else really matters. Any questions on that so far? The M here is the molecular mass, the mass of one single molecule. Molar mass is the mass of one mole, but we're not talking about a mole of molecules yet. We're still focusing on just this one molecule, regardless of whether there are other molecules or not. The thing is, though, molar mass and molecular mass are easy to convert back and forth. You just multiply or divide by Avogadro's number. Because the molar mass is the mass of 600 quintillion molecules. So you just divide by 600 quintillion, or hextillion, 6 times 10 to the 23rd, to get the mass of one molecule. So that's the energy of one molecule, 1/2 kBt times either the number of modes of the type you care about, if you want a specific type of energy for that molecule, or the total number of modes of that molecule if you want the entire thermal energy of one molecule. But presumably we're not looking at just one molecule. Presumably we want to scale this up to many molecules. So you can take the energy of one molecule and multiply by the number of molecules. So the energy of, usually we use capital N for number of molecules. We can take the energy we have so far, and multiply that by the number of molecules, capital N. And you could think of this as a unit conversion thing also. Looking at what we have so far, we've got energy per mode. We're multiplying by modes per molecule. And then we're multiplying that by molecules in the whole sample. Molecules per whole sample. So when we multiply these, modes and modes cancel out, molecules and molecules cancel out, we're left with energy for the whole sample. And that is, of course, if you know how many molecules there are in the sample. But usually we don't describe a sample in terms of number of molecules. We instead count number of what? Because the number of molecules is usually ludicrously large, right? We wouldn't want to have to count up how many molecules. Instead, we would describe a sample as having, well, molecules are particles. Usually in terms of Avogadro's number, right? We'd count it up in terms of moles. You wouldn't want to say this sample has 30 times 10 to the third molecules. You just say it has 6 moles or 5 moles. Because 1 mole means Avogadro's number particles. It's very much like, for instance, dozen. Dozen just means 12 of something. Mole just means 600 times, or 6 times 10 to the 23rd of something. So if we use Avogadro's number as a conversion factor, instead of saying molecules in the whole sample, let's say we use molecules in 1 mole. Molecules per mole is specifically Avogadro's number. So the energy per mole is energy per mode times modes per molecule to get energy per molecule times molecules per mole. So this whole thing altogether tells us energy per mole. And that can be very useful because it standardizes it. Instead of looking at 1 particle or some arbitrary numbers of particles, we're scaling it up to exactly 1 mole of the substance. And then if we want to know the amount for several moles, we just multiply this by number of moles. We could just multiply by n, the number of moles. And that just gives us the thermal energy of the whole thing. So Na is the number of molecules in 1 mole, which is standardized. Little n we usually use to represent the number of moles in the sample. So here we are further multiplying by number of moles in the sample, which means moles and moles cancel out. We're left with energy for the whole sample. And this now gives us a general formula for thermal energy of a sample measured in number of moles. Any questions on that so far? And there's a further simplification we can do here, or not so much a simplification, but a substitution. We have here Boltzmann's constant, which is extremely small. It's talking about the energy of individual atoms or individual modes within the molecules. And we also have Avogadro's number, which is ludicrously large. It's the number of molecules in 1 mole. But those show up multiplied together frequently enough that it's worthwhile to have an abbreviation set aside for that. And that abbreviation is R, which is Boltzmann's constant times Avogadro's number. So anytime we see Boltzmann's constant times Avogadro's number, you can replace that with R. And likewise, anytime you see R, you could split it up into Boltzmann's constant times Avogadro's number. This is in fact the same R we see in the ideal gas law, PV equals nRT. So this is called the ideal gas constant. And it is basically the same idea as Boltzmann's constant. Boltzmann's constant is energy per Kelvin in 1 mode. R is talking about energy per Kelvin in 1 mole of particles. So it's really just scaling it up. Boltzmann's constant talks about energy at the molecular level. R scales that up to be talking about energy at the molar level, energy of an entire mole of molecules, which is why Avogadro's constant is the constant of proportionality here. So if we make that substitution, Kb times Na is R. And then let's see what else we have. We've got a times temperature. We've got a times number of modes. We've got a times N, which I'm going to put over here, and also a times 1/2. I'll just put that down here. So this is another much more compact way we can write out our formula for thermal energy. And I think this is probably the most useful variant of all of these. These are all basically the same equation, just written out in different ways and expanded to different amounts of particles. But this, I think, is probably the most useful way to write it because it's much more compact. It deals precisely with just number of moles, temperature, and how many modes each molecule has, which might be an average thing if they're not all the same number of modes. And that tells you the thermal energy. We could also apply a delta to both sides. What's the only thing over here that you would expect to be changing? Yeah, presumably the temperature. Everything else is a constant and can be factored out of the delta. So we just get N times R times delta T times number of modes over 2. So there's a useful formula for change in thermal energy. Also, this formula we've got so far works for any substance, but where else have you seen nRT? What else is that equal to? Yeah, that's the ideal gas law, right? That's equal to pressure times volume. If it's a gas, of course. Like I said, this formula works for any substance. If it happens to be a gas, though, we can replace nRT with PV. So for a gas, we can also use E thermal equals nRT just replaced with pressure times volume, and then we still have number of modes over 2. So this can also be very useful because this is now a formula for thermal energy that doesn't require us to know the temperature, and also doesn't require us to know how many molecules, how many modes there are. All we need to know is the amount of space the gas takes up and the pressure it's experiencing, and of course the number of modes. But this allows us to make an equivalence between pressure and volume, which are easy to measure, number of modes, which we might already know or might not, and thermal energy. In fact, you can even use this to figure out information about the number of modes. Let's say you know the pressure and volume of the gas and you know how much energy it has. You could solve for number of modes. And let's say you solve for number of modes and you find that it is 7. What does that suggest about the gas if you know that the molecule has 7 modes? Yeah, presumably it's diatomic with all the modes active. Or alternatively, let's say you find the number of modes is only 3, and it stays 3 no matter what temperature you're at. What sort of gas would have only 3 modes? Right, it'd be monoatomic. And so you can figure out information about the individual molecules, whether they're monoatomic or polyatomic, and even the shape, whether it's linear or nonlinear, just by looking at how the pressure and volume are related to the energy of the gas. So you can perform macroscopic experiments, perform experiments on this gas and measuring its pressure, its volume, its energy, and figure out information about the microscopic behavior, what's going on with the individual molecules. So this is one of the very powerful results of this, that we can use this and measurable macroscopic information to get conclusions about what's going on with the individual molecules. Any questions on that so far?
Quick thing, but just to make sure in the Bost equation, the number of modes is not the total, right?
It's for one molecule.
Okay.
Rather, so one molecule, not the entire system.
Okay.
The entire system would basically have number of modes times N times Avogadro's number all put together. Mm-hmm. So if you combine number of modes times Avogadro's number times number of moles, this would tell you the total number of modes in the entire system. Because that's modes, again, you could think of this in terms of the units. Modes per molecule times molecules per mole times moles in the whole sample. So that would give you number of modes in the whole sample.
Mm-hmm. Sure,
but we don't really care so much about the total number of modes in the sample. We're just using that to build a formula for thermal energy, or perhaps more usefully, change in thermal energy. Any other questions on that so far? And speaking of microscopic measurements versus macroscopic measurements, let's compare this formula to another formula we had earlier for thermal energy. Because we've got this microscopic formula, microscopic in the sense of dealing with individual molecules. We got delta E thermal equals this one with the delta nr delta T times number of modes over 2. But of course, that's not the only formula for thermal energy. Earlier in the quarter, at the very beginning, we were looking at another formula for thermal energy, more macroscopically. Not really considering the individual atoms and molecules, but just the everyday experience of add heat to an object, its temperature goes up. What was our usual formula for delta E thermal at the beginning of the quarter? Well, heat is what causes the change in thermal energy. But how would you calculate how much the thermal energy changes? Yeah, usually MC delta T, mass times specific heat times delta temperature. That's one way anyway. But note that in this formula, we're not talking about mass. We're measuring the amount of substance in number of moles. We can do the same thing here. Instead of talking about the mass times the specific heat per kilogram times the delta temperature, we could instead use number of moles times the specific heat per mole, also known as the molar specific heat or molar specific heat capacity, times the change in temperature. And this one I think is going to be more useful in this context because now both of these formulas involve number of moles. Because both mass and number of moles are just two different ways of talking about how much of the substance there is. And number of moles I think is going to be more convenient here. So that gives us two different formulas for delta E thermal. Are these formulas talking about two different kinds of thermal energy, or is it all just thermal energy? It's all just thermal energy, right? I mean, this one's talking about the energy that the substance has because of its temperature. This was talking about the energy that the molecules in the substance have because of the temperature. But it's still just the energy it has because of the temperature. It's just a difference of, are we looking at just the whole object as one big thing, or are we considering the behavior of the molecules in the object? But the object is made of molecules, so these are still talking about the same thing. And if these are two different formulas for the same thing, what can we do with those formulas? Yeah, we can set these formulas equal to each other. This is one of the most useful things you can do in a case like this. Anytime you know that two formulas, two mathematical expressions equal the same thing, like in this case, this formula equals delta E thermal, and this formula also equals the same delta E thermal, we can set those formulas equal to each other to get more information about the situation. So let's try that. Let's take our microscopic formula in terms of the individual molecules and how many modes they have, and set that equal to the macroscopic formula, number of moles times this property we would just look up on a data table, times delta temperature. And now we can get even more information out of this, because what shows up on both sides of the equation here? Yeah, we have n and delta T on both sides. So if we divide both sides by n, and also divide both sides by delta T, a whole bunch of stuff is going to cancel out. N's cancel out, delta T's cancel out on both sides. And all that's left is molar specific heat. That is the specific heat, or the heat capacity of 1 mole of the substance. In the same way that the usual specific heat we're looking at in terms of mass is the heat capacity of 1 kilogram of the substance, molar specific heat is the heat capacity of 1 mole of the substance. It's just heat capacity standardized to a fixed amount. Meanwhile, on the other side, all we have is R times number of modes over 2. So this actually provides a formula for the molar specific heat we should expect for any substance. You take any substance you want. If you know the number of modes, you can just take the number of modes, and again, this is per molecule, multiply by the ideal gas constant, which is about 8.31, divide by 2, and that tells you the molar specific heat. So we can use this to predict the molar specific heat for any substance. And this also provides a more conceptual explanation of why different substances have different specific heats. The only reason why you'd have a different molar specific heat is because the substances have different number of modes per molecule. Any questions on that so far? Then let's try a quick example of this. Let's say we have, let's say a noble gas, such as helium. How many modes would you expect a noble gas to have per molecule, or per atom, I should say? If the whole gas is just an individual helium atom, and then lots more of those, but far apart, how many modes does one helium atom have? Yeah, it should just be 3. This one atom can move in the y direction, in the x direction, and in the z direction. So we have 3 translational modes, and that's it. It can't rotate because it's just a single point, so rotation wouldn't really be meaningful. It has no internal vibrational modes because there's nothing to vibrate against if it's just a single atom. And there's no external vibrational modes. It can't interact with its neighbors because in a gas, the neighbors are too far apart. So 3 modes, and that's it. We should then be able to find its molar specific heat by just taking R, which is 8.31 joules per Kelvin mole, times number of modes, which is 3, and then dividing by 2. So that'll be 8.31 over 2 would be 4.155 times 3, so it'd be 12.6. Is that right? 12.3. About 12.4, 12.5. So this is the molar specific heat we should expect for not only helium, but any noble gas. So if you look up the specific heat per mole of a noble gas, it should be pretty close to this. And again, you can apply this to any substance as long as you know the number of modes per particle. Any questions on that so far? Then let's try that with nitrogen again. Let's try nitrogen gas. How many modes would you expect the nitrogen gas to have per molecule? Seven modes per molecule, so we've got 7 modes. So we fill in 7 for number of modes, and we get 7R over 2, or 3.5R. And we often just leave this in terms of R. We might leave it as just 7R over 2 to make it obvious that 7 is the number of modes, or reduce it to 3.5R. You'll also see this sometimes referred to as CVM, CV mole. The V here just means we're assuming the gas remains at constant volume during this process. So I should probably put that here as well. CV mole means the gas is being held at constant volume during this process. It's not allowed to expand or contract. The reason we make that assumption is if the gas is expanding or contracting, like let's say you've got a container with a piston and the gas expands. That means the piston is moving as the gas pushes on it. And if you've got a push on a moving object, what does that count as? A force on a moving object counts as, pressure is how the force is spread out, but force times distance tells you what information? Yeah, that's work. If the gas is expanding, that means the gas is doing work to lift the piston. And work is energy leaving the system. That complicates things. We don't want to have to worry about work leaving the system because the gas is expanding, or work entering the system because the gas is being compressed. So by holding the gas at constant volume, that allows us to control the experiment. We don't want the gas's volume to change. We want to make sure that the only thing going on is adding heat or removing heat. We don't want to have to worry about work yet. We're going to look into the effects of work later on when we get to the pressure volume graphs. But for now, we're assuming the volume does not change. So all that's happening is adding heat or removing heat. We are actually looking at the entire molecule here. This molecule has 7 modes. If you're looking at just one atom, that atom would only have 3 kinetic energy modes and that's it. But nitrogen doesn't exist as single atoms. Nitrogen exists in these diatomic molecules. And this molecule has 7 modes. It's got 3 ways to move translationally because it could be moving in any of the 3 dimensions. It's also got 2 ways to rotate. It can rotate around a vertical axis. It can rotate around this horizontal axis. But this horizontal axis doesn't count because rotating around its own axis of symmetry is no meaningful change. So 3 translational modes, 2 rotational modes, and also 2 internal vibrational modes with the atoms vibrating against each other inside the molecule. So the 7 modes is the entire molecule altogether. Any other questions on that so far? So specific heat would be 3.5 R. And again, you could fill in 8.31 joules per Kelvin mole for R and multiply that out. But it's often more practical to just leave it in terms of R, as if R were the unit of measurement here. However, that's assuming the N2 has 7 modes. Does this nitrogen molecule always have 7 modes? What situation what has to be true in order to have all 7 modes active? Yeah, it's got to be a high enough temperature for all of those modes to be active. If it's too cold, then the molecule can't vibrate on the inside. If it's really cold, it can't even rotate. It's just fixed in a particular orientation, able to drift through space, but not able to rotate. So this heat capacity, this 3.5 R molar heat capacity, only is true at very high temperatures. At colder temperatures, maybe we only have 5 modes. Maybe we're at room temperature and we've got the 3 translational and 2 rotational, but no vibrational modes. So maybe we've got 5 modes, so we'd have 5R over 2, so we'd have 2.5R. So the molar heat capacity actually changes depending on the temperature. If you're looking at just small changes in temperature, like just a few degrees, it's not enough to make a difference. But if you're talking about a very large change in temperature, maybe you're heating it up from like 300 Kelvin to 400 Kelvin to 500 Kelvin, you're going to be activating some modes. You're going from, let's say, room temperature, you'd have the 3 translational and 2 rotational, and that's it, to a very high temperature, you're activating more modes, and that increases the heat capacity, which means as it goes up in temperature, it's going to get more difficult to get 1 more degree of temperature because there's now more modes, so you need to give energy to extra modes, and that takes extra energy. Any other questions on that so far? And this ties into the graph that someone was asking about earlier. The graph that you may have seen in one of the discussion labs was a graph of temperature versus heat capacity. And it may have written it as CVM over R. The idea is instead of worrying about the actual value of R, we just take all these specific heats and divide them by R. So instead of calling this 3.5 R, we're going to divide by R and just call it 3.5. So if we have 3.5 as a value on the graph, that really means 3.5 R, which really means 7 modes. So we know at very high temperatures, we should expect 7 modes in this nitrogen, and therefore the heat capacity per mole would be 3.5 R. But what about at very low temperatures? And presumably these would have actual numbers in Kelvin. But let's say the temperature is just very, very cold. How many modes would you expect this to have if the temperature is very cold? If it's even colder than that? Because I would expect 5 at about room temperature. At some medium temperature, you'd have 5 modes. 5 modes, 5 over 2 would be 2.5 R. So at medium temperatures, you'd have like about room temperature, around 300 Kelvin. I would expect 5 modes, therefore 2.5 R. But yeah, at extremely cold temperatures, the rotational modes freeze out also. So if it's very, very cold, the only thing the molecule can do is move around in space. So you've got the 3 translational modes and that's it. So at very cold temperatures, you've got 3 modes. So you get 3R over 2, which will be 1.5 R. So 1.5 R. And again, on this graph, they're dividing out the R so they can write the numbers more simply on the axis. So at very low temperatures, we have only 1.5 R as the heat capacity. So that would be 3 points on the graph anyway. And if you're looking at just one atom or one molecule, then that one molecule stays at 3 modes until it has enough energy to activate, jumping up to 5. And then stays at 5 until it has enough energy to start vibrating. And then it stays at 7 forever. So any one molecule is either at 3 or 5 or 7. But of course, we're not looking at just one molecule. We're looking at many molecules. So instead of just jumping up like this, it's not an all at once thing. It's not like all the molecules are just translating and then suddenly they all get enough energy to rotate. It's more like you increase the temperature and then maybe one more is able to start rotating. So that brings up the average a little bit. Any given molecule has 3 or 5 or 7. The in-between values just don't work. But if you have just one more molecule start rotating, that increases the average number of modes. And then increase the temperature a little more, you increase the average number of modes. So if you zoom in really close, this is going to look kind of like a stair-step graph as one more molecule, one more molecule, one more molecule starts rotating. But there's so many molecules that there are many, many, many very tiny stair steps, and this essentially just forms a straight line, or sometimes a curve, depending on the situation. But it's going to be smooth and continuous. It doesn't actually look like stair steps unless you were able to zoom in so close that you would notice individual molecules start to activate. But for all practical purposes, in a large sample, this may as well be a smooth curve or a straight line. But all this represents is as you raise the temperature, you're activating the extra modes of more and more molecules. And that raises the average number of modes per molecule, and therefore raises the heat capacity. And different substances will have different curves because they activate those energies at different temperature rates. But they're all going to be increasing because as you raise the temperature, you're increasing the number of modes available. Except, of course, for noble gases, which would just be stuck at 3 forever. Any other questions on that? All right, then have a good weekend, and I will see you next time.
Quick thing, but I was wondering if you still have some time.
Mm-hmm.
I was wondering if we could clarify the K equals 1/2 MV2 equation again.
The 1/2, what was that?
1/2 MV2, MV squared.
Oh, is the kinetic energy?
Yeah.
Yeah, that's just the formula for kinetic energy in general.
I was wondering
the kinetic energy of any one object is 1/2 times the mass of the object times the speed of the object squared.
So for one substance, would the mass be however many moles of it times the mass, the molar mass?
In this case, we're probably talking about the speed of an individual molecule, so you use mass of that one molecule. We don't really care about the other molecules nearby. We're just looking at this one molecule, so you'd use the mass of one molecule.
But if you were like comparing the entire substance, then would you take into account of that?
I don't think the entire substance is really moving, though, because the entire substance is just sitting there. It's just that the individual molecules inside are vibrating.
Oh, what if it was a gas?
Even then, you've got like this container of gas. The gas is the container is not moving. You've just got these particles moving around inside the container.
Oh, okay.
So
I see. Thank you.
we presumably just be looking at the individual molecules one at a time.
Mm-hmm.
Any other questions on that?
No, that's my only question. Thank you.
You're welcome. See you next time.
You too.